Hello, my name's Graham King. I'm the product manager for DesAcc EMEA Limited, and today I'm going to be speaking to you about dirty data, biased data, and the challenge they pose for machine learning and artificial intelligence. This is an area we're very much interested in. I've been working in AI and data science for the last 3 years and 18 years overall in the area of health IT and interoperability. DesAcc EMEA are based in Bath in the United Kingdom, but we work globally, and we are experienced with the challenges of handling healthcare data at scale. Using our deep understanding of how data is created and stored, we extract, standardize, and move data between healthcare systems worldwide. So, our main concern about AI and imaging is that models won't generalize, that there are concerns about bias emerging more and more, as we see in studies, and that both of these will breed mistrust amongst users, purchasers, and the public. That was illustrated in this study, which looked at deep learning model learning to diagnose pneumonia in chest x-rays. The researchers found that when they trained the artificial intelligence model at one hospital and then moved it to another one for testing and tested it with that hospital's data, there was really quite bad generalization of the model, even though it performed well at the initial site. And they found that as they crossed the 3 sites involved in the study. And there's the reference there. We'll come back to that later. We believe that the root cause is that good quality data is too scarce and that the solution needs to lie in platforms with multiple capabilities to overcome this scarcity. And I'll talk about what those capabilities are during this talk. So, why is imaging data scarce? Well, we believe the reason is fourfold. The resources to accurately label data are intensive, and we'll talk about what that means in a moment. De-identification of data is challenging, particularly in medical imaging, where the DICOM format contains patient information and other identifying information within every single image as metadata tags. Thirdly, because of dirty data, and I'll expand on what that means when we come to talk about that. And fourthly, there is a great need to combine data if it's to be useful for machines to learn from. So, labeling and annotating image data. We have to teach the AI model what it's seeing. It's not just enough to supply the image. We have to supply it with data alongside the image so that it can learn what's normal and what's not. Here's an example of weak labeling. So we said that there's lung carcinoma in this image, but we've not said where, and we've not said what type. So that's an example of weak labeling. And that could have been done by a single expert or an expert panel, or even by extracting keywords from report text, which is a method that's been used quite widely. Strong annotation is saying it's a non-small cell lung cancer that's visible, and also drawing a region of interest around that. So there's a proper polygon region of interest. It could just be a bounding box, or it could be a point value saying, look here. Again, done by a single expert, more commonly by an expert panel, not possible by report text extraction because somebody's got to draw the box around it. So human intervention is needed here. And then there's the gold standard. We often want what's called the ground truth, the best quality reference data for what's seen in the image. And in this case, it's actually going to be in the pathology. A biopsy was done, and the histopathology biopsy tells us that it's actually adenocarcinoma. So combined with the region of interest and the pathology information, this is a very strong form of labeling and annotation. However, it's also a very expensive form. We've had to extract data from 2 different systems, or maybe 3 if we're using the report, and radiologist labeling of the data is time consuming and therefore expensive. Report extraction also needs to be used with caution. The system has got to be able to distinguish between different types of labels. So it's not enough to say pneumonia or lung cancer, because it might be possible lung cancer, or lung cancer has been ruled out, or pneumonia has been ruled out, or maybe pneumonia or lung cancer are just one diagnosis amongst many. So report text extraction needs to be carefully looked at. And this piece of research by Oakden-Rayner shows some of the dangers of labels in some of the existing publicly available data sets. De-identification is well known. We've got to be able to remove identifying information, not just about the patient, but also potentially physicians and operators, equipment, and the institution. And we need to remove these if studies are to be properly blinded. And we need to remove it not just from the image metadata, the tags within the image, but also from potentially from the pixel data itself and maybe also from the report text where there could be patient, physician, and institution identifiers present. An example of the way we must be careful in de-identification is if we consider that we want a longitudinal record of patients' images and the date of their birth, and if we have one death date, we need to be able to obfuscate these dates. So we don't want the patient's real birth date to appear in the image. However, we also want to be able to preserve the correct number of days between all these imaging events in the patient's timeline, the longitudinal journey. So we can move all the dates back 35 days in this example to obfuscate the birth date, and we change all the exam dates correspondingly. So that means altering a number of different DICOM date tags in order to make that happen. And any half-decent piece of de-identification software for DICOM can do that for you. It's the longitudinal dates option, it's called. And if it's following the DICOM de-identification profile fully, we'll actually see a tag telling us that's happened in the DICOM. So that's all good so far. Is that enough? Well, there are other fields in the DICOM that can also contain date information, but they're not present as date variable types. So here we see the SOP instance unique identifier also based on a date. Again, that's mostly okay. Any reasonable piece of de-identification software will either give you an option or automatically change and write new instance unique identifiers for the exam to get rid of those. However, date information can be lurking elsewhere. Here's a real example from an ultrasound, and here's a date hiding as a short string field in the perform procedure step ID. So if we keep that date in, if we show that the DICOM has been altered with the dates modified option, and we have a new study date that's been written by the de-identifier, we can actually use the difference between this value here on screen and the modified study date to show the number of days that the study has been biased backwards or forwards by, and we can use that as a key to decode the patient's true date of birth. So we've got to consider factors like this. Also, if we want to hide institution and other identifying information like accession number, beware that they don't just hide in the institution accession number fields. Here's the requested procedure ID field within an MRI that had already been through a de-identifier software, I should add. And because this is an English site, the institution is identified by a 3-letter prefix on the accession number, which I've blacked out. And that actually allows us to identify the institution and the accession number in one fell swoop. Some of this is not a problem. For feeding the images, AI algorithms actually often don't use or want the DICOM. They'll construct a PNG or other kind of image file from the DICOM and just use that, so they're not even reading the tags. However, upstream stages of the pipeline for AI may still take the DICOM, and we still need to access the DICOM for mining and finding and preparing our data for AI and machine learning. So issues still remain even with the AI algorithm not taking in DICOM. The pixel data itself can contain identifying information, as can some of the textual information that we might be feeding into the AI pipeline. So pixel data, I think these are well known, so I'm not going to labor the point too long. Ultrasound has the patient banner that needs de-identified by masking or pixelation, and it's not always at the top, so sometimes it needs to be a manual or semi-manual process to remove this. Secondary capture in the image study, images encapsulated PDFs can all contain text data that contains identifying information, either as pixels, or in the case of the PDF, as text. And there's the good old CT dose slide, which often contains details about the operator, the institution, and the patient's name. In the case of the secondary capture and the dose slide, sometimes our only choice will be to jettison those. That's unfortunate because they contain information that may still be useful for mining and finding and feeding artificial intelligence. So if we're going to use those, we need to find quite complex ways of de-identifying those. So my takeaways from this section are: know thy data, inspect it, understand other places where you might find identifying information to be hiding. But that's unfortunately time consuming to identify all those, and alter de-identification routines to take care of additional fields that you weren't expecting, and maybe even having to do manual removal of pixel data from the images or secondary capture themselves. So I said to speak about dirty data, and I want to consider 3 aspects of dirty data: invalid values, different representations for the same concept, and missing values. This is particularly important when thinking about selecting imaging cohorts, both invalid information and varied representation of the same concept. I'm going to think about body part. I'm going to look briefly at MR protocols. So body part. This is from some research that DesAcc did a few years ago with one institution, and you can see all these exams in green and red. All the ones in red are examples of where the body part examined tag was invalid in terms of DICOM allowable vocabulary. So why is that a problem? Well, if we consider that we're looking for lower spine exams, you can see there's an L spine value in green. We'd find just a little over 34,500 exams under that category if we were searching using body part L spine. However, we'd miss nearly 157,000 L underscore spine values. That's not not a valid value if we were only looking for the correct DICOM field categories. So if this is not corrected, then there will be problems trying to identify a full cohort of data. This very recent white paper actually proposes the use of anatomic region sequence, which has kind of superseded body part examined in terms of the currency of the DICOM standard, a very flexible field that supports SNOMED and other coding systems and supports multiple body parts instead of just one in the previous body part examined field. It mainly addresses being able to use this to drive proper workflow and reporting, but would be equally appropriate for driving more granular machine learning based on body part and filtering for studies based on body part. And there's the reference there. MR protocols. This is obviously an area where we actively would love to use machine learning, multi-slice imaging, many images, different types of images. It would be great to be able to process those through machines. And you'd think that if we were doing research on MR and machine learning, we could quite easily ask the question, find me T1 brain MRs and get an answer. It's not as simple as it seems. Protocol information currently isn't really standardized. It's free text, and these three different fields could all contain information about exactly what scan protocol was used to acquire the series, and these vary quite considerably. They're rarely stored, indexed, or searchable in the PACS VNA. They stay in the DICOM, but they don't get pulled into the PACS or the VNA's database that you can then search on them and do queries. And they're highly variable by institution, vendor. Even the same scanner from the same manufacturer can be different with different instances of the device, can vary by protocol, and even sometimes by operator. Missing data, so this is another aspect of dirty data. I'm going to take an example from outside imaging here. And this is the only time in this presentation I'll talk about the COVID-19 pandemic. This piece of research, excellent piece of research, highlights the importance of the NHS's centralized data for being able to do large-scale population health. The Open Safely study was able to take 70 million records from systems run by the firm TPP in the UK, mainly in England, actually. So they were able to take that information and look at factors relating to risk of death. So we know from the media that there is some kind of link between ethnicity and greater risk of mortality. And this study did indeed confirm that. There was certainly an increased hazard ratio. However, there was missing data. Ethnicity was missing for approximately 26% of all the patients that were eligible to be included in the analysis. That meant that ethnicity was missing for 4.5 million patients. So our takeaways from this: invalid values reduce the data we can find and also kind of pollute it. Varied values need standardized if we're to answer questions in machine learning and find, again, a full cohort of studies. The best way to correct that would be at source, but I think we have to accept that for the time being, and if we want to use legacy data from the last decade or more, we've got to correct after the fact as well. Missing values need to be accounted for, and a valuable strategy for dealing with all of these is, first of all, to know your data and being able to catalog it. So looking for solutions that help us understand the state our data's in, the varied values which exist, if we're then to be able to understand how to correct it. And also combining data is going to be really important. We talked before about ground truth and labeling in our first section. We want to be able to combine radiology reports, maybe also histopathology reports, and even data from other systems and the patient's wider electronic health record. All of that requires some kind of pseudonymized linking identifier that brings in data governance, that brings in data protection, because pseudonymized data is still regarded as personal data. So we've got to look at ways of doing that, which both allow combining of data and retains patient privacy. And there is, of course, a tension between those two aims. Accessing data from other places often involves looking at silos, and by that I mean systems where there's no interface to query, there's no expertise to query if there is a reporting or statistical package. Proprietary data schemas make it very difficult to work out what data you're supposed to be getting and from where. And like in our example of the MR protocols, data's stored by a system, maybe in the raw files on disk, but isn't surfaced in a way that can be easily queried through a database. So our takeaways here is that breaking open silos and technology switching extract raw data will be important if we want to get high quality reference and outcome data. And data does also need an identifier which allows linking, yet also protects privacy. So sources of bias is what I want to look at in the next half of this presentation. And this is a very important quote from Ivana Bartoletti, who's an AI leader and ethics advocate currently working for Deloitte. Data isn't neutral. The capture, processing, and classification of data reflects priorities and inherent bias within our cultures and societies who are collecting the data. So even at the very beginning, data isn't neutral. There can be selection bias in who captures it, from whom, and how it's classified. This study looked at emergency department imaging in the United States using a very large data set that covers a range of hospitals and patients who are both privately insured, on government schemes, self-paid, uninsured. There's the reference there. And they found that non-white patients were statistically less likely to receive imaging in the emergency department than white patients. The difference was most marked between white and black ethnicity, 51.3 against 43.6. And that was even after correcting for other factors like patient mix and institution level factors. So random retrospective samples may still contain inherent biases is really the lesson here. This paper is recommended reading, and I want to think about wrong inferences that AI can make. AI machine learning are all about making connections and spotting patterns in data, but not all the patterns and correlations are necessarily causal or valid. So this very useful article is a great guide and contains a great checklist in one of the graphical boxes in it on factors to look for about bias and elimination of bias. They say readers of AI articles should be aware of the potential of machine learning to overfit the development dataset by learning patterns that appear only in that dataset. And I want to speak about one particular great example of that in the study I mentioned right at the beginning. So this was looking at diagnosing pneumonia using deep learning from data from 3 different institutions in the United States. One was a large public data set of the National Institutes of Health, one was Mount Sinai Hospital, and one was the Indiana University healthcare system. So they found that their AI model was actually able to predict what hospital it was without knowing what a hospital was because of the markers in the X-ray exam. So the chest X-ray uses specific position markers at each site. They looked quite different, whether they were metallically applied as clips onto the imaging cassette or added as annotations later on electronically. And because one of the hospitals, Mount Sinai, had quite a different prevalence of pneumonia, much greater prevalence than the other 2 hospitals, the AI was actually learning to make a correlation between the presence of this marker and the incidence of pneumonia. So by engineering cohorts of varying prevalence, they found that it was actually using that marker to predict pneumonia. It was actually ascribing a weight to those markers in terms of its prediction. And they found that worse than that, the AI didn't even require that marker. It was also able to look at subtle differences in acquisition protocol, image processing, or the distribution pipeline, which confirms what radiologists and radiographers have long said, is that it's possible to identify each different vendor's piece of equipment from the way it looks. So it's not just humans who can see this, the machines can see it too. And there's the reference there. And even more fine-grained than that, at Mount Sinai, the AI models, the convolutional neural networks, as they call them, could actually separate tests that were done on portable machines from inpatient wards versus images that were done in the outpatient or emergency setting on upright X-ray machines at Mount Sinai with 100% accuracy. And that those patient groups had significantly different prevalence of pneumonia. So again, it was learning the distinction between those two image types and weighting accordingly. And the distinction was actually fairly marked when they went in to investigate why. The outpatient emergency department exams were done on a machine that used your typical white on black imaging type, whereas the portables were using black on white. And that was something they only discovered after the fact. So models were still using this to weight the prediction of pneumonia, even though that wasn't a causal factor. So takeaways is that models don't always generalize, as that study showed, and that beware confounders. Know thy data is important here. They only found out this distinction between the two image types after the fact, and really it would have been better they've been able to correct the inverse monochrome behavior there prior to image processing in order to try and present the machine learning with the same thing. But also another factor of this study is they did everything right. They tried to make the AI model explainable. They were able to use heat maps to pick out that the areas of the image that were particularly being correlated with learning were these markers in the corner, yet it still happened. Spectrum bias is another thing I want to talk about. Very common when you read the AI literature and imaging. A disease, condition, or sign has a distinct prevalence amongst the population being tested. And it's not uncommon for AI to be trained and even tested with an enriched data set. And what do I mean by that? Well, another word for it is case control. So if we consider that a condition has a typical prevalence where maybe 4 out of 200 imaging exams will show a positive or abnormal sign, but the other 196 out of 200 will be negative or normal. We often see that AI has been trained or even tested with maybe 100 of each. So that's really significantly weighting the data set towards the abnormal. And as I said, we often call this case control. This article in the RSNA's Radiology, very useful, a recommended reading for everybody about evaluating clinical performance of AI based on studies and things to look for. And the authors of that state that development of an algorithm for medical diagnosis or prediction, especially an algorithm in which deep neural networks are used, typically requires a huge data set. So if bias is to be avoided, data at scale, which we've already seen as a problem, is going to be necessary. Retrospective collection of radiologic imaging data set to try and get that big data set is still prone to spectrum bias because, of course, not everybody gets radiology, particularly for ionizing radiation studies. It's not right to just be scanning or imaging the general population in order to try and get a larger data set. So we've got to bear in mind that referral criteria exist. So there's layers of possible exclusion, and there's a very helpful diagram in the article that shows all the layers at which a patient can be excluded. So one thing I'd certainly recommend is when you're reading literature, look for this kind of diagram to show where patients are being excluded and at how many steps. Good articles will be upfront and publish exclusion and inclusion criteria. So I want to think, just as we're beginning to draw to a close, of this study, a very useful study that looked at positron emission tomography and Alzheimer's disease and tried to use a deep learning model to predict correlation there. So they used a model, and their literature includes this diagram showing the exclusion criteria. One of the things they had to make sure they excluded was they'd used a test data set called ADNI of about 1,000 images to train their model to read PET images. And so they had to exclude those from the test imaging set. And here you can see they've been up front. There were only 40 images in their test data set once they'd excluded all the other criteria. And a study should be honest about its limitations. I often jump straight to the limitations section of any article I'm reading. And this one was very frank. It said this was a highly selected cohort. All patients had to be referred. The neurologist must have decided that PET was going to be appropriate for clinical management, and that the algorithm's performance in a more general patient population remains untested and unproven. And just as a bit of an aside, one of the other findings of this study was that even though, again, they'd done everything right, they used what's called a saliency map to try and show which features of the image were important for the algorithm in making its prediction. They actually showed that it was looking at the whole brain, and there was no one kind of smoking gun human interpretable biomarker that could be used as a kind of definitive correlation. So even though this AI had really striven to be explainable, I think we have to accept that sometimes AI won't always be fully explainable in the way that we'd like, just as a radiologist's brain and the conclusions it draws are not always easily explainable either. It doesn't mean that the diagnosis is wrong. It just means that we can't always be 100% transparent about how brains and neural networks are working. So in summary, our data manifesto believes that the solution lies in platforms with multiple capabilities which can help overcome this scarcity and help reveal and hopefully overcome bias. Data at scale is going to be really important for overcoming bias, but that means acquiring good labels, reliable labels from existing data. That means de-identification is going to be really important, particularly in the data preparation and data finding stages. Dealing with dirty data is going to be really important, correcting, standardizing, and augmenting it. However, a first step to all of that is cataloging what's there and understanding the dirtiness of the data and what values exist and what values are missing. Being able to extract and standardize locked-in data from other silo systems is going to be really important if we want to combine data to get a rich record, to get that reference data and that ground truth. And also, to be able to understand potential biases in the data set, we need to be able to catalog data, understand where things like ethnicity and gender are missing, understand that the representation of those categories in the data set is skewed compared to the general population, and also being able to acquire data from different populations in different institutions so that we can show that validation testing of AI models is done on diverse data sets. So thank you very much for listening to this presentation and watching. Look forward to joining you in the question and answer.